Okay, so as I said, this is the part which was not in the original outline, but it still continues the same theme, mostly looking at non-equilibrium dynamics. But now we will shift from traditional solid-state systems more towards ultracold atoms, which is kind of synthetic matter. And I'll try to at least introduce some of the key ideas or kind of key facts about ultracold atoms for people who don't know the field. But it will not be kind of truly representative about the field as a whole. I'll focus on sort of just certain classes of questions, which is polaronic phenomena, and also on things which can be, as you'll see, again, just in continuation of what we were doing, I'll sort of really bring up cases which we can study theoretically using variational wave functions, something that has very close connection to what we discussed so far. Okay, but let me start with sort of like commenting on when we talk about ultracold atoms, how cold is ultracold. You know, one of the comments one can make is, well, of course, that's very subjective. You know, since I grew up in Novosibirsk, so probably my standard of ultracold are much lower than for most people in the world. But I think you will agree that in the case of cold atoms, we really talk about ultracold temperatures, since we talk about sub-nanokelvin. And the best illustration of the kind of the range of kind of physical phenomena that can be studied with cold atoms, but on the other hand, in generality, examples that I really like is example of the study of the Higgs excitation. So let me remind you that usually when you hear Higgs, you think of the high energy experiments, right? So this is this plot of this figure of proton-proton collision, and you see this kind of bump is kind of resonance scattering, which corresponds to exciting Higgs mode. And what's interesting is that within a week of the announcement of observation of Higgs at LHC, there was a paper by the Munich group observing Higgs-like excitation in the superfluid state of bosons in an optical lattice. So in their case, instead of colliding particles, they were adding energy to the system just by modulating the optical lattice, and they were looking energy absorbed, and they also see resonant energy absorption. And in fact, in this case, the Higgs is also tunable. You can see that by going close to the quantum critical point, the energy of the Higgs mode can be tuned all the way to 0. But what's remarkable is that in the case of high energy experiments, to see the Higgs excitation, they had to go to energies which are 12 orders of magnitude higher than the room temperature. And in the case of cold atoms, we're talking about energies and temperatures which are 12 orders of magnitude lower than the room temperature. So we talk about phenomena separated by 24 orders of magnitude, yet they are universal. And that's also kind of, in some sense, also the motivation for a lot of things that we're doing, is that even though we have such, you know, difference of energy scales, like we're looking at cold atoms, but they can provide insight in particular things happening at our physical scales, say, when we talk about strongly correlated electron systems. Okay, so let me sort of say a few words about the history of ultracold atoms. So it's all started with Bose-Einstein condensation of alkali atoms in '95. And this is one of the most common experiments in this field. So you have atoms in a trap, and then you do time of flight. And you can think about time of flight as basically free expansion of atoms, right? So if you started with atoms in a trap, then you let atoms expand to sizes which are much, much larger than the original system size. Therefore, if you take an image after the expansion, then you are really measuring velocity distribution inside the trap, right? Because you can assume that atoms are flying out as free particles. So when you look at these images, they actually can be understood as velocity distributions inside the trap. And at high temperature, okay, we see some kind of like Maxwell distribution, but then as the temperature is lowered, you see this kind of bimodal distribution. There is a thermal cloud, and then there is a condensate. So this is a macroscopic occupation of the state of the lowest kinetic energy, right? And at lowest temperatures, we just see all the atoms essentially in the condensate. Okay, so what was appealing to begin with in the field of cold atoms is that they are really weakly interacting, right? So you can say BEC is something that we have seen for helium-4. So what's new here? Well, what's new is that the typical distance between atoms is, so it's thousands of angstroms, and it's orders of magnitude larger than the typical scattering length, which is kind of the length scale which defines the strength of interaction. And so as a result, you have weakly interacting systems. You can do very controlled theory, unlike helium-4, where, of course, microscopic theory is very complicated. And what comes together with these large length scales, just by the usual, energy is 1 over mass length scale squared, is small temperatures. So, for these numbers, we talk about microkelvin, and like now in optical lattices, we saw they go to even sub-nanokelvin temperatures. So, okay, people had some fun with weakly interacting particles for a few years, but then, it kind of gets boring, and people decided to go back to strongly interacting systems. But of course, the difference now is that interactions are tunable. And so there are two most common ways of tuning microscopic interaction. The first one is a so-called Feshbach resonance, where you can when you can have the scattering length go through infinity. The second way is to use optical lattice. So this is kind of an artificial periodic potential. So we have standing waves of laser beams, and then what's left from kinetic energy of atoms is tunneling. So by having a lattice, we are suppressing kinetic energy, and also particles have to sit on top of each other in the minimum of the potential, so we amplify interactions. Okay, so let me, for those who haven't seen, haven't thought about Feshbach physics, it's a very simple idea. So if you go back to your undergraduate quantum mechanics, you realize that, okay, if we take two particles interacting with each other, let's say we go to the center of mass frame so that we're only left with kind of the relative motion of the two particles. So it's really a single particle problem. In the single particle problem, we have attractive potential. And then if we start tuning the strength of this attractive potential, we start creating more and more bound states, right? And every time you get a new bound state into the system, the scattering length goes through infinity. So, and in fact, when the bound state just appears, right, the scattering length is positive. So I usually think about it as kind of second-order perturbation theory. So you have two particles from the continuum approaching each other, right? And then there is a bound state nearby. And then by second-order perturbation theory, you can sort of couple this these kind of propagating states into localized state. And as usual in the second-order perturbation theory, there is some kind of level repulsion, right? So as a result, if you have a localized state which is has very small energy, then it will push the state which is above it, right? Which is extended states. It will push it higher in energy, and that pushing of the extended state higher in energy is exactly what positive scattering length describes. If, on the other hand, the bound state is still in the continuum, right? Then you can think about two particles coming at zero energy. They're also kind of coupling kind of virtually into the state which is still above in energy, right? It did not become a true bound state, and that pushes the energy lower, and that's why we get a negative scattering length. And so this line, exactly when the bound state is at zero energy, is what's called unitarity. So the scattering length is formally infinite. Okay, and let's say what you will see often in the theoretical discussion is that instead of working with true microscopic interaction, which in fact is more complicated than this simple kind of Lorentzian, you see contact interaction. It turns out that if you, as you know, like if you introduce contact interaction, you need a cutoff in 3D, right? Contact interaction does not make sense without the high momentum cutoff or high energy cutoff. And so there is a simple, if you take a delta function with sort of sharp momentum cutoff at lambda, then there is a simple relation between the scattering length, microscopic interaction, and the cutoff. So you see it's kind of, in principle, in 3 dimensions, this integral diverges, right? So that's exactly why we need a cutoff. Like in 3D, you cannot just take a delta function because you would get like formal divergence. You have to say, oh, my momentum is less than something. And physically, the way to think about the scattering length compared to microscopic interaction, so we have 2 particles coming in at low energies. And then they can virtually go to higher energies and then come back, right? And we're trying to reconstruct the scattering amplitude of low energy particles by including all of those virtual scatterings to higher energy states. And unfortunately, the phase space grows very fast. That's why we need a cutoff, right? So really, the scattering length, as you remember, described the scattering amplitude at low energies, and it involves multiple microscopic interaction, sort of multiple scattering to higher energy states. Okay, so, and as I said, we want to focus on exploring polaron physics with ultra-cold atoms. So what we focus on for polarons were kind of lattice polarons, like, say, electron, which distorts a lattice or excites phonons. But in fact, it's much more general, right? So we know that in many correlated systems, actually, we have strong interplay of charge and spin degrees of freedom, so charge carriers are dressed in some kind of magnetic screening cloud. So these are all examples of the so-called Bose-polarons, right, when a particle is dressed in a cloud of bosonic excitations, but we can also have FERMI pollarons, and that's something which is relevant, say, to X-ray. So when we photoexcite electron from the core orbital to the conduction band, then that's something that we talked about in Riggs, right? This generates particle Hall excitation. Or let's say Kondo effect that we talked about, that's also a kind of example of the fermionic polaron. Okay, so what are the kind of tools that people have been using? So one of the tools is RF spectroscopy. So one of the simplest way of doing this is, and that's say how it was done in experiment by Rudy Grimm originally, and Martin, and like dependently Martin Twirline and Michael Curl. So you start, say, with a mixture of 2 internal states of atoms, right? And usually they come, with hyperfine state, which can take very large values. So you have many internal states. And so by tuning magnetic field, you can take certain combinations strongly interacting, certain combinations weakly interacting. So here you start with this mixture, but it's actually imbalanced mixture. You have very few of these green atoms, right? And so this is like the majority, whereas this can be thought of as impurities, but these impurities are really weakly interacting to begin with. But then you apply an RF pulse, which takes this, let's say, state 1 into state 3, but now state 3 is strongly interacting with 2. Therefore, when we make an RF transition from state 1 to state 3, it's not like we're simply, it's not sort of like a single particle physics, it's not transition between 2 levels, because as soon as this atom goes into state 3, it immediately starts interacting very strongly with the majority fermions. And that's why this, and sort of you can say it excites kind of like particle Hall excitation in the Fermi sea. And that's why the spectrum is much richer. So you can see, so this is, let's say basically, this is where we see the positive scattering length, right? And it goes up. And that's also, but we know that when we come close to resonance, then we also have a bound state. And here you see a bound state. And this is the site of the negative scattering length. So in terminology, usually this is called attractive kind of polaron branch. This is repulsive polaron branch. Or you can do kind of a more, an experiment which is more atomic in its spirit, but as we'll see, it's closely connected to this. And this is to take, again, think of 2 states of an impurity atom. And in one state, it is non-interacting with the surrounding fermions, like basically this one. And now for simplicity, let's assume that this is just fixed impurity is either very heavy or we have an optical potential, which is very strong, just acting on the impurity. So because it doesn't interact with the surrounding fermions, we just have this unperturbed Fermi sea. And then we make a sudden transition, right? Let's say we basically, if we flip the internal state, right, of this impurity atom to the state 3, it will start scattering the fermions. right? And that's what is shown here, right? We basically start generating many particle Hall excitations. And what you can do in atomic physics, you can do in the ferrometric probe. You can actually make a superposition of spin down and spin up states and look at how coherence between them is changing in time. So that's something that we'll discuss later. So these are kind of examples of how one can study fermionic polarons. Then there are bosonic polarons. This is, say, experiments from Florence. So they have, it's a one-dimensional system of rubidium atoms, and they have potassium impurities, which originally are pinned, right? So they're localized, but then the spinning potential is removed. And actually, in fact, these potassium atoms have to oscillate, but they don't oscillate basically in free space. They oscillate in the sea of bosonic atoms. So they really oscillate as bosopolarons. And experimentally, you can study the frequency of these oscillations or damping of these oscillations. Then one can also do RF spectroscopy, which very similar to what we discussed for fermions. You can do it for bosons. And as actually we'll talk later, that there is much more interesting physics. So in theory here, that's something, kind of collaboration that started with Alexei and his former student, Yulia. And again, this has been also been studied experimentally in Arcus, in the group of Arcus. Or sort of another interesting, very surprising experiments that was done in Innsbruck, in which you take an impurity atom, but not in a weakly interacting Bose gas, but in a strongly interacting Bose gas. And if you take strongly interacting Bose gas, then bosons, they sort of become like hardcore bosons. They become like fermions. And it turns out that in some sense, they almost make a crystal-like structure. And so then if you try to move an impurity through this crystal structure, what you find, not through this crystal, it's a liquid of bosons, they're just strongly interacting bosons. What you find is that the momentum of these impurities, instead of just monotonically increasing, undergoes this reflection. So in solid state physics, you remember this, like you have this so-called Bloch oscillation. If you have periodic potential, if you try to accelerate a particle, it will undergo reflection by reciprocal lattice vector. So here you see this physics of Bloch oscillations, which you usually associate to kind of external, truly periodic potential, but here it happens for an impurity on the strongly interacting Bose gas, which is fundamentally fluid. Okay, so let me just take you through some of the examples of what has been done. So let's talk about, say, exploring Fermi polarons. And this has been kind of a long-standing problem in condensed matter, for example, is to really study dynamics on, say, short time scale, on the scales comparable to Fermi energies. And the problem is Fermi energies are so high for electrons that we're talking about ridiculously short time. There are just no, like, experimental techniques are just very hard in this range. But we already said that for cold atoms, energy scales are much smaller, which means that the time scales are much longer. And so it's much easier to do experiments. In fact, you can change microscopic parameters on time scales which are much shorter than the intrinsic energy scale of the cold atomic systems. And that is, so you'll see what allows to study kind of dynamics of Fermi polarons. Okay, so one of the motivations for looking at Fermi polarons is to explore the physics of Anderson orthogonality. So this is one of the key concepts of condensed matter physics. Let me remind you how it goes. So it's basically a statement that if I have like a ground state of fermions, you know, let's say in a box, and then a ground state of fermions in the same box but with a single impurity, then the overlap of the two ground states in the thermodynamic limit is 0, even if it's really a single impurity. It's like a weak perturbation. No matter how weak this perturbation is, we will find that the overlap, right, approaches 0 as the system size goes to 0. So let me just sort of give you an idea of why this is the case. So let's think about fermions in a box, right? We occupy all the states with energies less than k Fermi. Right? Okay, well, so far so good. Now let's add a scattering potential, right, like an impurity somewhere. And as we said, it starts scattering, starts generating particle-Hall excitations. Let me do something very naive. I just include one particle-Hall excitation, right? So I take one fermion from below the Fermi energy, right, and I scatter it above the Fermi energy. And of course, like it's perturbation theory, so I have to put matrix correction to the wave function has matrix element and energy denominator, right? And then I have to normalize it. And I have to sum, I'm including one particle-Hall pair, but I need to include all kinds of particle-Hall pairs that I can, right? So it's kind of the lowest order perturbation in the scattering potential V. So now let me just calculate the overlap between my initial wave function and the wave function, which has just first order correction due to the scattering potential. And you can immediately see that this correction, right, okay, I basically have to take the square of this correction in the numerator, right, and this means that I have a square of the matrix element divided by the energy denominator squared. Now let's make, and again, I remind you that this state, like over n with sum over states below the Fermi energy, and over m over states above the Fermi energy, right, so which is shown here. And so let's assume that our matrix element do not depend on energy, right? So we can replace the summation or just by integration over energy. We have density of states. But look at this energy integral. So you see that when energies approach 0, right, epsilon n approaches 0 from below, epsilon m approaches it from above. And so we will, in principle, we will have it's an infinite integral, right, unless we regularize it. And the only quantity that it, sort of helps us avoid this infinity is finite level spacing, right? Because if I'm in a finite box, right, I do not really have, like, energy is a completely continuous variable. There is a finite discretization in energy, which is set by the size of the box, right? And therefore, basically, this log, which you can immediately see just from the dimensional counting of this integral, we see that this overlap, right, just diverges logarithmically in the system size, right, or in level spacing. Okay, this was first order, and then if you actually then you go to high order, you'll get log squared and so on. And if you then sort of sum up all of these divergences, actually you will get something which is like exponent of a log, which gives a power law. And so that's the result. That's the canonical orthogonality catastrophe, the overlap of the ground state without the scattering potential and with the scattering potential, right, is a power law of the system size. Okay, so another way of thinking, well, what's it doing? Yeah, okay, let me skip this part. Now you can ask, okay, that's the ground state. What does it have to do with dynamics? So here that actually turns out that there is a very interesting quantity. So we start with the Fermi C. Now we evolve with the Hamiltonian, right, that has an impurity potential. And then we take an overlap back on the initial state. And actually this now decays as a power law in time, just the same way as the overlap of two ground states decayed. The way to understand it is if we switch on the impurity, right, we generate particle-Hall excitation, which run away with the Fermi velocity. So you can easily convert time into length scale just by multiplying by Fermi velocity. And it's kind of like the overlap is now just coming from the overlap of, you know, this readjusted ground state where the perturbation had time to propagate over a distance v Fermi times t. Okay, and so this power law actually is expected to have very strong implications for things like, say, absorption, like for X-ray. That if you, electrons absorb an electron, if X-ray leads to exciting electron from the core orbital to the conduction band, then this core Hall, right, will scatter all of the fermions, and this should modify the absorption spectrum. So. This is an understanding of this, right? This kind of power law. This goes back to Phil Anderson and Nazier and Dominicis in the 60s. Okay, so actually, let's go back to this setup, right, with the impurity. So it turns out that, you know, like in condensed matter, you really study this just only in frequency domain, right? So either in some kind of like X-ray, then there are sort of like transport experiments where instead of frequency you get voltage, but it's really kind of like a Fourier space. But in cold atoms, you can really study this in time. And the way to do this is basically what sort of we discussed before. So, and in fact, that's what we discussed before is the kind of canonical kind of Ramsey sequence in atomic physics. So you start with an impurity atom in one of the states, right? We said it's a state which does not interact with the Fermi gas, right? So the Fermi gas is just happy even though there is an impurity. And then we do what's known as pi half pulse, right? We prepare a superposition of the impurity spin down and up. So it's kind of, it's like a cat, right? It's a simple cat, right? An impurity is just down and up. It's the same for MEC in both cases. But then after we prepared such a state, spin-up state of the impurity is actually doing a lot of scattering, right? So it generates many particle Hall excitation. Therefore, it evolves, right? So this kind of cat becomes a much more complicated cat because one kind of component of the cat is generating infinite number of particle Hall excitations, right? So if we let some time, actually, the difference between the two states become very large. And we can measure it by doing the second pi half pulse. And basically what the second pi half pulse does, it converts Sx to Sz and then measures it. But fundamentally, it's basically just now a measurement of this overlap, right? Remember, this object which we said, that's what, say, Anderson and Nazier and Dominicis introduced to describe, let's say, X-ray scattering. So here, by doing Ramsey sequence, you can measure it directly in time, right? Just by doing this Ramsey interference. And one question you can ask is, well, OK, but we understand this physics like from the 60s. Is there anything new? Well, the answer is yes, actually, there is something new. So this is work which really started when Dima Abanin was still at Harvard. So and he actually taught us a lot about, I really learned most of what I know about orthogonality catastrophe from him. But let's just calculate. You know, we really take this model of impurity, like heavy impurity. We do this pi half sequence, and we look at the decay of the Schloss-Schmidt echo. And one of the things which we didn't expect was that in addition to this power law decay, you also see very strong oscillations on the scale of a Fermi. Why did people not talk about this before? Well, in solid-state physics, why usually the argument was always, oh, the only thing that's universal is kind of long distance. But what's happening at shorter times, well, it really depends on details of interaction. But, you know, like in reality, we're dealing with Coulomb interaction between electrons. Who knows, you know, how complicated it is. You know, there is screening and so on. By contrast, in cold atoms, well, you actually do know microscopic interactions. So if I give you a scattering length, then I can tell you about you know, the entire energy dependence of the scattering amplitude. Therefore, we can talk about universality, right, of the Schloss-Schmidt echo at all time scales, not just at long time scales. In fact, okay, let me maybe skip. So it turns out that if you think about this Ramsey interference, you know, like the domain of what was studied in condensate was really this long times, let's say power law decays. But in cold atoms, like even the short time has very interesting information about, let's say, few body physics. And in fact, these oscillations have a very interesting kind of and simple physical explanation. You know, the usual orthogonality catastrophe is just a statement that impurity generates many particle Hall pairs near the Fermi surface. But in reality, if you have a strong potential, you can generate not just excitations near the Fermi C, but also you can generate one excitation from the bottom of the Fermi C. The way to understand this is as follows. So let's say we had unperturbed single particle levels. Then we introduced a potential which, let's say, is attractive, right? So we have states which, sorry, you can't see it very well, but the energy, kind of single particle states move down. And so then if you just look at the biggest overlap of the initial state with the new state, well, all the atoms just kind of go to the same state, like the lowest energy state goes to the lowest energy state, and so on. And we just maybe generate a few kind of cheapest excitation, right? Because it would cost us more energy to excite from somewhere in the middle of the spectrum above the Fermi energy. But when we talk about strong interactions, let's say at unitarity, if you think about the way single particle shifts, it's actually shift in such a way that single particle levels are exactly halfway between the original ones. Therefore, if you think about how the original wave function, like how the original electrons shift, for them the overlap is basically the same to go to states kind of states which shifted low in energy or states which moved up in energy. And if they all move up in energy, then you have this low-lying excitation left at the bottom of the Fermi sea. And therefore, this is actually an important feature of orthogonality catastrophe for strong interactions, the possibility of this scattering channel, which leaves sort of a deeply lying excitation, which is at the bottom of the Fermi surface. So, and that's kind of is responsible for these oscillations on the scale of a Fermi. Okay, and in fact, okay, there are, yeah, maybe I'll already commented on this. So this is something you can study in Ramsey, you can study in frequency. Okay, in terms of theoretical tools, so actually, you know, this problem is fundamentally a single particle problem, right? So because it's like if the impurity is infinitely heavy, when we switch on its interaction with the impurities, it's like we suddenly switch on the scattering potential. So therefore, the way to study it is the same, say, Gaussian wave functions, which we discussed before, right? So you can just evolve, let's say, covariance matrices, or you can do it slightly differently. So there is a functional determinant approach. Okay, I'll not go through the details, just give you the idea that, you know, if you have non-interacting fermions, then you know that if you, like Gaussian state, like is a slated determinant state, right? You just take single particle states and then you anti-symmetrize. So now if you're only switching on single particle potential, then it's enough to keep track of the evolution of single particle states because you know that slated determinant state will stay a slated determinant. The wave function must remain totally antisymmetric. So effectively, you can translate the problem from dynamics in the Fock space of, you know, many particle problems to dynamics of single particle eigenstates. But after you evolve single particle states in time, you then have to reassemble a slated determinant. And there is a powerful formalism which does it, but it's completely equivalent to what we discussed before. And, you know, so recently, all of this was taken just from the domain of, you know, theoretical studies to experiments. So these are experiments of Rudy Grimm's group in Innsbruck. This is exactly this kind of Ramsey interference experiment, and you can see that, in fact, temperatures at this point in those experiments has been high. Now they have much lower temperatures. And so at this temperature, it's difficult to see this kind of orthogonality catastrophe in the sense of power law, but they see this very strong oscillations on the scale of a Fermi, something that we said is very hard to see in traditional solid state physics. So let's see, how much time do I have? Till the break.
It's 35, so it's 10 minutes.
Oh, okay. 10 minutes?
Before the short break.
Okay. Okay, so let me actually...
But we can break now if you wish.
No, actually, okay, yeah, no, that's fine. Just to sort of get some idea. So one of the actually interesting questions that has been addressed is, like in the context of, say, Fermi polarons, is a competition between molecular states and molecules. So let me give you the gist of the problem. So you have an impurity atom which has strong attractive interactions. So if attraction is very, is sufficiently strong, you can imagine that there will be a bound state, right? So that's a possibility of molecular solution. Like an impurity will bind just one fermion, but because of the Pauli principle, once impurity binds one fermion, it essentially cannot interact with the other fermions. Or it can do something else. It can actually interact weakly, but with many fermions at once. That's the idea of the polaron, right?
Just terminology. I thought the first case is just called single-side polaron.
There's no lattice here. It's continuum.
Well, in crystals it's called single-side polaron.
Okay, I don't know. Like in cold atoms, it's called a molecule because it's truly a molecule. Right? It's something that is adiabatically connected to a molecular state in vacuum.
Okay.
So, okay, it's interesting. Okay, so how would you then call a regular polaron?
Multi-sub polaron, of course.
No, but you see, like you kind of single site, and is there a phase transition between the two?
No.
Okay, then it's not the same. In this case, it's a true phase transition, because you see the quasi-particle weight. If you do sort of the analog of RPS, the quasi-particle weight for the polaron is finite. It has a finite overlap with basically like a free particle, like a free impurity on top of the Fermi sea. the overlap is still of the order of 1. Whereas in the case of a molecule, if you have a molecule at a finite momentum, then which means that impurity atom has amplitude of 1 over n to be in any momentum state. Therefore, the quasi-particle residue is 1 over the system size.
Let me put it in a weaker statement. I don't know about phase transition. Okay, so.
But again, it's like in this, like the question is, can you define a property that is discontinuous? So here, the discontinuous quantity is a quasi-particle residue. Okay, so this is something that has been studied using RF spectroscopy. Again, just an idea is that you do RF spectroscopy. So in this case, right, unlike what we discussed before, you already start with a strongly interacting mixture. So you ask whether these impurities you just prepare them and let them make whatever ground state they want with the majority atoms, right? And this can be a molecular state, this can be a polaronic state. And then you do RF spectroscopy into a weakly interacting state. And you can do it either from the majority atoms or from the impurity atoms. And when you see, so this red and blue lines, they correspond to this RF spectra for majority and minority. And when you see that both of them have a peak at finite energy, this means we're dealing with molecules, right? It costs us the same amount of energy to break a molecule. But then as you go to a polaronic regime, you actually find that you see a peak for the impurity atoms, but this peak for the majority atom basically disappears, which means that there is no true bound state for the majority atom. So that's the polaronic regime. So here you can really see as a sharp change in the absorption spectrum. So actually, this was in 3D. In 2D, physics turns out to be different. So there, although it's still somewhat controversial, but with sort of simple approximation, you find that polarons are always low in energies in molecules, right? And again, people have explored this both experimentally and theoretically, and found good agreement. Okay, so what is interesting is that usually we when we talk about connection between cold atoms and solid state physics, then most of kind of inspiration and motivation comes from condensed matter physics to cold atoms, right? What are the interesting systems? But here it's an example of where information was flowing the other way. So after we analyzed, we know how the absorption spectrum looks like in the case of Fermi polarons. Then you can examine a seemingly very different system. So this is transition metal dichalcogenides. It's something that people are very interested in these days. So for practical purposes, think about it as graphene with a gap, right? And so it has very special features like electron-electron interactions are stronger than in traditional gallium arsenide, and that's why people are very interested in excitons. So kind of basically redoing a lot of optics that was done in traditional semiconductors, now in the case of gallium arsenide. And then one of the experiments that was done in Atachi Mamogu's group was to just basically create excitons, but do it not in the kind of the basic setup when you have a semiconductor, when you just have a filled valence band and empty conduction band, but start varying the density of electrons in the conduction band. And then you see this kind of basically, it's like a spectrum, right? So how do you see this absorption spectrum as a function of gate voltage, which is like a density of electrons? And you see these two peaks. Well, and then your immediate reaction is, we've seen this before. That's RF spectrum of ultracold atoms, right? Basically of the Fermi polaron. And indeed, it turns out that we can understand the spectrum as really kind of repulsive and attractive polaron. That interaction between excitons and electrons is happens to be very close to a Feshbach resonance, to unitarity, and that's why we get this physics of Fermi polaron. And one can use wave functions from that were used in cold atoms to actually describe, let's say, the spectra used in transition metal dichalcogenides. Talk about something which is not non-equilibrium physics. Now we'll be talking about equilibrium, but it's really kind of a very exciting recent development in cold atoms, so I can't resist sharing it with you. And this basically addresses one of the most long-standing problems in condensed metaphysics, and this is the Hubbard model. So just to remind you, it's a very simple lattice model. So we have fermions hopping on a lattice, right? And we have on-site repulsion. It's believed to be the to contain the most essential blocks for physics of high TC cuprates. And this is also a model which can be realized using ultracold atoms in optical lattices. And we already talked about that there is some kind of interesting phase diagram where we, like for the real materials, but we still don't really know whether kind of Hubbard model, like if we really study these microscopic models, and there is so much disagreement about the phase diagram, whether it contains all the features which we see in experiments on cuprates. That's why understanding the Hubbard model is very crucial to understanding of strongly correlated electron systems, and in particular high-TC cuprates. Okay, and then so there are several groups which have been working on this. So today I'll mostly focus on experimental results of Manuel Bloch's group and Marcus Greiner's group. Okay, so this is basically the type of things that I'll describe today. I'll start by one-dimensional systems. Okay, one-dimensional systems have an advantage that we know pretty much everything about them. And what you will see is experiments which demonstrate in a very striking way the concept of spin-charge separation in 1D. And then we will talk about, so this is about a couple of years old, and then the most recent experiments involve analysis now of interplay of spin and charge in 2 dimensions, and so we'll see how the picture of magnetic polarons. So the theme of polarons is really kind of the key theme in what we're discussing. How can we think about magnetic polarons in the Hubbard model, and what's the insights that we're getting now from experiments. Okay, so one thing that I want to mention is that now there is a remarkable new tool in experiments, and this is a so-called quantum microscope. So basically, for those who didn't follow the field, it's a possibility of measuring, of taking snapshots of the entire many-body wave functions. You know, it's like a theory stream where you take this interacting problem of fermions and you take a measurement and you know where every fermion is, right? So it's not, like usually when we think about correlation functions, we just talk about 2-point correlation function. But here, you basically know where all the particles are. So you get much more information than available in traditional measurements, and as you'll see, this provides kind of new insight into the physics of strongly correlated systems. Also, like when we compare it to theoretical numerical results, we will often use not the original Hubbard model, but a very close relative, which is so-called TJ model. Basically, it's an idea that if U is sufficiently large, then you can basically rule out double occupancies because they're very high energy state, but what's left from those high energies, from integrating out high energies, is magnetic exchange interactions. So therefore, that's really the kind of the model that we will use as a theory, but as you'll see, it does a good job for our purposes. Okay, so let's talk about 1D first, and like if you haven't heard about spin-charge separation, now you will see kind of very simple physical picture of how it emerges. So let's start first in the case when there is no doping. So we have one fermion on every side. So it turns out that in 1D, even at 0 temperature, you cannot have a kind of a broken symmetry at 0 temperature. So the right way to think about the ground state is to think about kind of fermions bound into singlets. They're not necessarily nearest neighbor singlets. They can extend further. But it's kind of less sufficiently short range. So now let's do the following. Let's remove one of the fermions, right? So we have an empty site here. Then in this case, we do not just have an empty site, right, which now used to have charge 1, now it's charge 0, but we also have unpaired fermion, right? And that's why when we talk about the state, we can say, oh, we have an extra charge 1 and an extra spin 1/2. So all the other spins are paired into singlets. And what is happening in 1D is that even if you start by preparing this kind of charge and spin 1/2, they start by being next to each other, they can actually separate very freely. And that's why we call this particle a holon, so it just carries a charge quantum number. But you see spins arrange themselves in a singlet around it. So there is no extra spin 1/2. But this missing spin 1/2 traveled elsewhere, right? And somewhere else we have a spin 1/2. And that's what's called a spinor, right? So in 1D, we just know that if we create an we create an electron, annihilate an electron, which gives us charge 1 and spin 1/2, they actually separate into two solitons. One soliton carries charge but no spin, and this carries spin but no charge. Right. But notice something quite interesting. We say that, oh, if we have a holon, that spins rearrange themselves into a singlet around it, and that obviously means very interesting types of correlations. So if we have two sites, right, so which are separated by two lattice constants across a hole, they actually are very likely to be in a singlet configuration, and that's very different from a classical antiferromagnetic state. Right? In a classical antiferromagnetic state, if you have two spins, when they're separated by two lattice constants, they have ferromagnetic correlations, right? But in the case when we have a hole and we have this kind of spin-charge separation, you see that we have kind of dominating antiferromagnetic correlations. So the nature of spin correlations changes. So there are several ways of understanding where this comes from. One of them is that actually, those of you who are familiar with so-called full de Ferrel type physics and superconductors, it's like an antiphase domains, because essentially what's happening is that basically we're saying, okay, if I have a hole, right, so here I have antiferromagnet, and here, instead of continuing the same type of an antiferromagnet, I actually kind of shift it by one lattice constant, right? So if I think about my Néel order parameter, right, so here on A sublattice I have up, on B sublattice I have down, so this is AB, so B was supposed to have spin down, right? But now it has spin up, and A sublattice was supposed to have spin up, now it has spin down. So the Néel order really changes sign, right, across a hole. So you can think about it as an idea that while if we have antiphase domain, if our order parameter, like say, like in the mean field, which really doesn't work in 1D, but at least qualitatively you can say, so order parameter changes sign, that makes it easy to put a quasi-particle in here. Okay, so let me maybe skip this. So it turns out that this is also present in higher dimensions, say for two-dimensional systems, but again, we'll not spend time on this. If people are interested, I be happy to answer. Actually, this physics is also present in high dimensions. But it turns out that in 1D, there is even more remarkable results. And the statement is that if I take a TG model, right, and then if I look at the spin part of the wave function at finite filling, then actually it looks the same as at half filling if provided that I remove all the sites that have holes in them. Right? So somehow that's what's called a squeeze space. I basically have to eliminate all the holes, and then I will recover exactly the same spin wave functions as if I did not dope the system. But of course, my holes can be anywhere, right? So basically, it's very hard to just, you know, if I think about correlations like between spins a certain distance away, whether I have a hole or I do not have a hole will change the correlations completely. It will change by a minus, right? So in order to see these kind of antiferromagnetic correlations, the same as we saw at half filling, we really have to know where all the holes are. And that's not something you can do in condensed matter, right? Because in condensed matter, we just measure two-point correlation functions. But in order to talk about the squeezed space, I have to know exactly where all of my particles are, right? I basically have to know infinite order correlation functions. Oh, but that's exactly what you get in experiments with ultracold atoms. You get a snapshot of the entire many-body wave functions, right? So this is from Emmanuel Bloch's group, and you can basically, the way they do is they sort of at the point of the measurement, they kind of spin up and spin down fermions, so going either up or down. Here you can see that if, like you see a particle in this kind of bottom box, then it was a spin down. If you see it in the upper box, it was spin up. You can have both of them, right? Then it's a doublon, or you can see none, right? Then it's a hole. And
Eugene,
yeah.
I ask impolite question.
Yes.
There are two ways to obtain these kinds of snapshots. First is true quantum measurement, many-body quantum measurement.
Yes.
So you have some... Yeah,
so many-body wave function.
Many-body wave function.
And you project.
Project it, you measure, you have this.
Yes.
Second is if you just have a classical system, say because of temperature or whatever, you measure, you have this. How do they distinguish between the two?
So it is actually, so this idea of, spin charge separation turns out to apply not only for the ground state, but even for finite temperatures. So as a result, the statement is that as long as I'm comparing these ensembles at the same temperature, like in the squeezed space, I'll have the same correlation as that half filling at the same temperature. So that's a remarkable property of TJ, that actually this the fact that basically the wave functions factorize is true not only for the ground state, but also for excited states.
But it's not clear, is their temperature correct?
Oh, it is. We know what the temperature is in these experiments. We can just look at how spins decay.
Is it really a quantum state or some classical discrete?
So I'm not going to show you these results. So let's say in 2D, this is a comparison that we have done, experiments by Marcus Greiner. So what he looked at was a two-dimensional system. In 2D, you can say, I cannot have long-range order at finite temperature, but you can go into the regime where correlation length is larger than your system size. So they were in this regime. And again, what they measure is, for example, not just the kind of correlation function, but they measure full distribution function of the staggered magnetization. So because you do measurements many times, and and you always measure in the z basis, and you see and you can obtain a histogram. This what's the probability of measuring certain magnitude of the of staggered magnetization, and you can show that it's inconsistent with the classical picture and consistent with the quantum picture. Okay, I'll be happy to tell you that yes, you can actually, because naively, classically, you would say, oh, I have, let's say, classical interferomagnet, it's just pointing in some random direction. You would get one form of distribution, so it would be more boxy-like. But they see a more rounded distribution, which only appears from the quantum solution. They see this difference. So it turns out that these experiments in, by Bloch's group, they are done at somewhat higher temperatures. So I don't know whether we would see this dramatic difference. But it's kind of interesting. These two groups, they have strength in different, Marcus's experiments. They are at lower temperatures, but they, as you will see, they do not have they cannot resolve simultaneously spin up and spin down. So Emmanuel can resolve spin up and spin down at the same time, but they're still at somewhat higher temperature. But it's just kind of a matter of time. So cool it further. Right, okay, and so this is kind of demonstration that what we were discussing. If we look at conventional measure of two-point correlation functions, you see that it's modified dramatically by doping, right? So half filling, right, this green line. Okay, we have antiferromagnetic correlations, nearest neighbor, then they become ferromagnetic, and then they decay. So it's exponential decay, that's what gives us the thermal length. As soon as we start doping, you can see that these kind of oscillations, they just wiped out very rapidly, right? We go to doping of 40% occupation number. We don't see any kind of oscillations. On the other hand, if we really define a squeezed space, right, we really extract, remove where all the holes are, and we just look at spin correlation in squeezed space, basically correlations remain the same no matter what the doping level is, right? It demonstrates that indeed, even if I were to just measure, two-point correlation functions, I would say, oh, I don't have any magnetic correlation, right? The decay, don't see that it's antiferromagnetic. I just have some smooth decay, but in squeezed space, we still see this very robust antiferromagnetic correlation. So you just have to sort of find this. It's a kind of hidden order, right? It's hidden by random positions of the hole. Okay, you can say it's 1D. In fact, we do know about this spin charge separation from earlier theoretical work, so that's not so interesting. What about 2D? That's something that we really don't understand. Okay, so In 2D, the situation is more interesting, so let me just tell you about some of the basic ideas. Let's try to do the same trick, right? We start with a classical antiferromagnetic state, up-down configuration. Then I make a single hole, right? And then I let this hole propagate, right? It propagates, you know, like it moves to the right, which means the spin down moves to the left. And you see something unpleasant happens. We used to have perfect antiferromagnetic correlation, but now this side, which used to have spin up, right, in antiferromagnet, because of the hole motion acquires spin down. So we have these bonds, right, which are now ferromagnetically aligned, whereas they used to be antiferromagnetically, right? So we have a kind of frustrated configuration. And in fact, as the hole keeps moving, this kind of frustrated configurations continue because now the spin up moves to the left. And you see now the spin up particles sort of like a misaligned, right? Because now they have ferromagnetic arrangement, whereas they were supposed to have antiferromagnetic. So therefore, you know, if we think about a spin where we start, yes?
To some extent, this argument applies also to 1D, right? At least the first.
No, but most of this frustrate, like, yeah, but it's a finite amount of energy. Here, what's crucial is that the further the hole propagates, the longer is the string. So the energy increases with the length. Right? So that's kind of the essential difference is that now if we think about a spin and a Holon, right, if the hole moves away from a spinon, you know, in 1D it was just a finite amount of energy. You paid it once and then you don't care, like spinon and Holon can move. But in 2D, as a Holon moves, this kind of the classical energy cost, magnetic energy cost gets larger and larger. So there is a string-like potential. And that's why we believe that they are bound. That's why there is no spin-charge separation in 2 dimensions. Well, in fact, this also gives a kind of a simple way of trying to understand this kind of the nature of this doped hole. So we say, well, basically, you know, as a hole moves, it leaves behind this kind of this pattern of flipped spins. And this increases the magnetic energy linearly. So let's think about it, just a particle. Basically, let's just keep track of the motion of a Holon because it's a much faster particle. So now if we want to label how it moves, you know, it's not like a motion of a particle in empty space, because in empty space, you just have to specify an instantaneous position of the particle, and then you know everything. But in this case, actually different trajectories correspond to different patterns of flipped spins, right? Because if let's say, a Holon goes this way or that way, it will be a different configuration that has been flipped, right? Therefore, we have to, when we think about the motion of a hole, we have to keep track of the entire trajectory and not just the final position. And that's why we label, we represent the motion of a hole as motion on this kind of the so-called beta lattice, right? So like from the first side, you can say the hole moves in 4 directions, and then it can go up or left. And so basically, you can see that there are no kind of like loops coming back, and that's because even if like even if a Holon makes a loop, it doesn't mean that we go back to the original configuration, because making a loop leaves behind, right, a kind of like a pattern of flipped spins. That's why it's different from not making a loop, right? That's why we label basically, it's kind of like this trajectory which just keeps going forward. And that's what's called beta lattice. And we know that the energy, as we said, magnetic energy increases linearly, like with the number of steps that we make on this lattice. So this should remind you of the kind of basic problems that you have in your undergraduate quantum mechanics. This is motion in a constant electric field, right? It's a Stark problem. Remember, you have, let's say, kinetic energy. You have potential, which is linear in x, right? If you have electric field, which is constant, then your electrostatic potential is E times x, right? And so, like in this Stark problem, you know that let's say you can just very easily construct something which has units of energy, which sets the scale for the energy excitation just by dimensional counting from electric field and mass. You can construct just this object which gives us energy. And now if we think about, you know, our problem, like this motion of a Holon, so the analog of 1 over mass is tunneling, right? And the analog of the electrical field is magnetic energy J. Therefore, we should construct the energy scale which is, by analogy with the Stark problem, is just tunneling to 1/3 and J exchange to 2/3. And you'll see that this kind of energy scale, in fact, shows up when we analyze magnetic polarons in 2 dimensions. Okay, so another analogy, so we already talked about analogy with kind of Stark problem in basic quantum mechanics. Another obvious analogy is with QCD, right? In QCD, if you think about mesons, mesons are bound states of 2 quarks, right? We know that they're always bound. If we try to separate them, then we get an energy which grows linearly. That's why we have a confinement. So that's kind of what we have here. When we try to separate spin and Hall, right, then there is energy that grows linearly. And so people sort of like Laughlin, Blanc, Manusakis, Strugman have been advocating this point of view. And in fact, when people do, let's say, analysis of spectral function of a hole, they find, often you see this pattern of kind of peaks which are separated by the same amount, which is kind of very similar to the problem like in a Stark ladder, right? You know, if you look at energy levels in a Stark ladder, you have this equally spaced states, equally spaced in energy, and that's what the kind of the Arcus spectrum looks like when people did numerics on the TGA model in the past. Another way to think about it is to say, oh, it's kind of like as a whole moves, it can just emit 1 magnon, 2 magnons, and so on. So anyway, we have this analogy with the quarks, but in fact, we can push this analogy even further than this was explored in condensed matter systems. Because if the way to understand, let's say, this spectrum, right, excitation spectrum from the point of view of, you know, this kind of 2 particles bound by a string, is to say, oh, these are like vibrational excitation of a string. Right, so somehow I know that in our case, like a holon is fast, it's moving around the spinon, and it has some ground state wave function. Or I can make an excitation where I sort of keeps the angular momentum of the holon around the spinon, but it goes to a higher vibrational energy. And that's these peaks that appear in the ARPA spectrum. But in fact, in QCD, you have another type of excitation, and this is to take the same 2 quarks but change the angular momentum, right? Because if you look at the kind of the quarks, you can the same combination of quarks, but for different angular momentum quantum number actually correspond to different mesons. And we can have exactly the same construction. If we look at a spin and a holon, we can get eigenstates of this bound spin on the holon at angular momentum 0, angular momentum 1 or 2, of course projected onto the lattice. In the usual kind of condensed matter setting, if we just think about ARPA's experiment, we do not have any matrix element to go to finite angular momentum states. But in cold atoms, because you have this freedom of, let's say, applying an isotropic perturbation, something that couples differently in x and y direction, we should be able to excite into analogs of this mesonic states at finite angular momentum. Okay, but let's move on and let's say, okay, so this is hopefully like this type of exploration analogy to QCD, something that we'll see in the future. But for now, let's just continue with what is available in experiments at the moment, right? So how do we see these magnetic polarons? And as we said, a very simple picture is to think of as a spinon as basically kind of a very slow particle, and then this holon, right, which has a certain finite binding potential, right? But then it moves around, so it's kind of we have a certain radius of its wave function, cannot travel too far because there is a confining potential. But within this radius, it's kind of doing a very random motion. It's exploring the entire vicinity of a spinon. And this you can put into an actual wave function. And of course, like as a holon moves, like what is important, remember, when a holon moves, it actually kind of reshuffles the spins. But we can use this wave function to calculate the energy of the polaron. And we can also compare to earlier results on quantum Monte Carlo. And first of all, notice the way it's plotted. So it's energy of the ground state energy of a single hole plotted in units of t divided by j over t to 2/3. Therefore, if we look at energy, it's really energy that scales like this linear slope essentially tells us that we have j to the power 2/3, t to the power 1/3, exactly what we saw from this analogy with the Stark problem, right? And so this kind of rational Monte Carlo, and this is this simple kind of picture that I gave you of the string wave function. We assume that the spin configuration is frozen, and it's just a hole which is doing a random walk. So it does a really good job, which agrees with quantum Monte Carlo for the energy of the polaron. It does a kind of very decent job for describing the dispersion. In particular, let's say there is a very kind of interesting feature of this magnetic polarons is that their minimum of the dispersion is at pi half rather than 0. Naively, if you have a polaron, right, like the bare particle has a minimum at 0, has energy minimum, sorry, at momentum 0. But if we think about kind of the dispersion of holes of magnetic polarons, it actually, the minimum is shifted to the antinodal points. And in fact, most of this dispersion, so if we change momentum, most of the energy changes come from the exchange energy rather than by hopping. Okay, but let's just utilize this unique tool of ultracold atoms, and this is the idea that we have, snapshots of the entire many-body wave functions. And of course, what makes this problem more complicated is that, remember, we said, okay, we have a spin and we have a hole, but this holon is it's bound, but it's moving very fast. So we have to average over all positions, right? That's what makes this kind of like a polaron-like picture. And as we said, as a holon moves, like it scrambles positions of the spin. So spin correlations are modified very strongly. So, okay, so how are they modified? Let's kind of look at, say, correlations which are next nearest neighbor, right? So in the kind of undoped case, while looking at the diagonal correlation, they should be, sorry, this is somewhat misleading. Okay, so somehow we're looking at correlations which are sort of away by two sides. Sorry, I think this was kind of a typo. We have antiferromagnetic configuration, right? But we know that if we look on the diagonal, we should have ferromagnetic correlations. But now, see, let's just look at what happens to these correlations as a whole moves. Because it reshuffled the spins. Now look at the spins on the diagonal. They now have antiferromagnetic correlations, right? So in the vicinity of the hole, we expect that these correlations are modified. And indeed, if we do, let's say, exact degradation rational Monte Carlo, okay, I'm not showing string theory, you can see that a wave, if you really now you think about the measurement where you say, okay, let me look at this diagonal correlations, right, as a function of distance to the hole. So far away from the hole, we should recover our case of undoped systems. Right, so we should have ferromagnetic correlation, which are positive. But when we come closer to the hole, we're really averaging, right, over these antiferromagnetic configurations and ferromagnetic configurations, so we should get 0. Right, so it's kind of, now it's not two-point correlation function. So we talk about correlations of two spins, but it's dependent on knowing where the hole is. So it's at least a 3-point correlation function. And so that's kind of the behavior that we expect, and indeed that's kind of like what is seen at the current stage in experiments. So the color is a color coding of correlations. You see it's ferromagnetic far away from, in this case they used a doublet rather than hole, but it doesn't matter. And then as you approach the hole, it actually changes from ferromagnetic to 0. Then another type of kind of nearest neighbor correlations, which again you would expect to be ferromagnetic away from the hole, right? It's again next nearest neighbor in the horizontal or vertical direction. But then if we come to the hole, we see that they can also acquire contribution, which is anti-ferromagnetic, right? So because across the hole, right, you see it's anti-ferromagnetic. And indeed, if you sort of compute, you expect this evolution of the like away. Sorry, sorry, I'm confusing you. So actually, in this case, these are nearest neighbor correlations, right? Sorry. these are nearest neighbor correlations, right? So nearest neighbor, they expect it far from the hole, they expect it to be anti-ferromagnetic. But close to the hole, you see, like close to the hole, now these nearest neighbors are ferromagnetic, these are ferromagnetic. So we sort of have to average between now some anti-ferromagnetic correlations, right, near the hole and ferromagnetic, so we should get 0. And again, that's what you expect theoretically. And sorry, there is a mismatch. Okay, sorry guys, I have the wrong picture. So this is actually, okay, so this is for nearest neighbor correlation, whereas these are experimental results, but that shows still next nearest neighbors, and it shows that it's ferromagnetic away, and it goes away from the hole, so well, the doublon is here, but it essentially becomes kind of, it goes to 0, or even anti-ferromagnetic close to the hole. So we see that these magnetic correlations really change around the hole. Okay, so this was kind of going from 2-point correlation function to 3-point correlation function. But in fact, we can introduce a new, like, sort of motivated by things like, machine learning pattern formation. We can even start thinking about new ways of analyzing experimental data. After all, every snapshot is just a bunch of data, right? So what you want to do is you want to extract, some patterns and see if they sort of make some sense to you. So now this is based on collaboration with Marcus's group. As I said earlier, the disadvantage of Marcus's experiments, they cannot simultaneously manage image spin-up and spin-down particles. So they can have measurements in which they image both particles at once but cannot resolve the spin. Or they can image spin-up particles only, or they can image spin-down particles only. So, but anyway, even with this, as you'll see, we can actually get quite interesting information. And the kind of information that we're after is to say, well, remember we said that as a whole moves, right, it leaves behind, right, let's say here, imagine that I start with a perfect anti-ferromagnetic configuration, right? So then as a whole moves, it leaves behind this kind of string of flipped spins. So therefore, I really see this kind of missing pattern, kind of deviation from a perfect checkerboard arrangement. And now what we know that from this kind of string picture, we had some wave function, right? That solution on the beta lattice, we had a certain wave function. So that gives for the whole, which basically gives us distribution in terms of the length of the string. And that's what we're trying to see. Can we actually see this string pattern, right, in the actual data? Well, this example was very particularly simple because it was TJZ model where we basically said, oh, I only have ZZ type of the interaction. I didn't have kind of spin flips. In reality, there are still flips. So my ground state does not correspond to the classical anti-ferromagnetic state. But it turns out that, like, okay, if you can, say, analyze on a smaller system, say 8 by 8 torus, and again, you are asking, okay, I see this kind of pattern, right? And I measure it in a Z basis. And then I sort of compare it to the best checkerboard that I have. And then I just focus on the difference with the perfect checkerboard. And this difference with the checkerboard, I ask whether this is consistent with having kind of holes which made the string-like excitations. Right, so, and then you can, okay, so this is what you expect just from the MRG calculation, right, that you would get a certain distribution of strings. So now, even when the hole is not moving, right, so you would get some distribution of strings. And that is simply reflects the fact that we now have like a full TJ model, right? We have some kind of spin flip process. It's not a classical anti-ferromagnet. So even if I measure the ground state of a quantum anti-ferromagnet, sometimes it will have flipped spins. That's why I can sort of spontaneously generate some of this kind of like string-like excitation, but I would still see the difference. As I start switching on the tunneling, I would still see the difference with the kind of the pattern of strings that I would get when my holes are allowed to move. Okay, and so in particular, let's say and so like say if I start increasing the tunneling, right, I should see the growth of the typical string length, just because I now like without tunneling, right, I just, if I have strings, I just random strings which come from the quantum motion. Maybe that's also a question that Alexei was asking, oh, is it kind of like, how do I see the quantum nature? Well, you can also see it in the distribution of the strings, kind of like what exactly are deviations from the classical antiferromagnetic state. But no, this excess strings that you get, that's really a result of the Hall motion. Okay, and that's roughly what you do like when you analyze the data, right? So that's, let's say, an image. Let's say that's an actual image. Let's say you just have spin up. And then you say, OK, let me find the best checkerboard that matches it. So because clearly, OK, this kind of looks like a checkerboard with just some defects. And so you can then, OK, so these are my defects, right, compared to the checkerboard. And now I analyze, so what kind of strings do I have? And we just choose one criteria for now, the length. Right, so this is a string of length 3, a string of length 1, of length 2, right? So we have this distribution. And then we just plot this distribution of length as a function of the length. And so this is just undoped system, right? And as we said, even in undoped system, we have a certain number of strings just which originate from quantum, well, this is finite temperature and thermal excitations of the Heisenberg model. Then we start adding finite doping. And so you see, OK, maybe it's hard to resolve this way. So the bottom line, right, that was our undoped system. That was undoped system. And then the upper points. But notice it's logarithmic curve. Even though the points look close to each other, I mean, we're actually talking almost an order of magnitude difference in the number of strings. Sorry, it's just not the best way of plotting this. And then you can ask, oh, but maybe if I just randomly scatter, you know, because I edit whole, this clearly is going to increase my counting of the strings, right? I start adding strings randomly. So this is, sorry, I start adding just holes randomly, right? Because that will also be a deviation from a perfect checkerboard. But that actually, it increases the counting, or it would increase the counting of strings, but not enough to explain the experiment. So clearly, the kind of the increase in the number of strings that we see in experiments is more than just randomly adding holes, right? And we know that, remember, like the hole really changes the nature of magnetic correlations around itself. And this is actually, if we use that simple model, that kind of string picture of spinning in a holon with a finite kind of string constant, right? We just saw on the beta lattice like a hopping with a string constant that and the coefficient that we extract, they're taking actually from the system at half filling, just from the knowledge of correlators at half filling. Okay, and this is, okay, probably like this, instead of looking at the distribution, let's just look at the kind of the average number of strings. And you can see this was undoped, right? So we had this background average number of strings, but as we have doping, this average number of string increases. And if we were simply adding randomly, you know, holes, you know, that would clearly not be enough to account for an increase in the number of strings. And that, again, is comparison to this picture of bound spinning and holon. As actually another test of you know, this kind of string picture, right? Because string picture of spinning and holon bound together in a frozen spin approximation, you can ask what happens to the spin configuration, to the spin correlations. So basically, again, just to remind you, the origin is if I look at, you know, let's say this, let's say at correlations, at nearest neighbor correlations. So, you know, these spins used to be antiferromagnetic, right? But now if the, as a whole moves, right, they now become next nearest neighbor. And they were supposed to be ferromagnetic, but now they are antiferromagnetic. And in fact, we know that at half filling, the nearest neighbor correlations are much stronger. So as a result, what you expect is that if a hole moves sufficiently, then you can even change the sign of next near of these diagonal correlations from ferromagnetic, it can become antiferromagnetic, right? Just because you are sort of, you get a finite amplitude of these correlations really originating from what used to be nearest neighbor, and nearest neighbor was much stronger correlation. And indeed, as a function of doping, you see that this kind of next nearest neighbor diagonal correlations function of doping should changes sign. So this experimental plot, and again, comparison to this kind of string picture, and that whereas if we just simply randomly scattered like holes, we would not see this change of sign. So anyway, it looks like, okay, if we analyze kind of magnetic correlation around a single hole, this picture of a frozen spin background and just a hole kind of messing up the spins sort of takes care of most of the data, right? Well, actually, here there is more. Okay, that's actually partially to what I was describing. You can also look at, let's say, not just magnetization, like the average value of magnetization, but full distribution function, right? If you take the snap, like if you measure the system many times, right, you can just see, okay, like from shot to shot, we'll have different values of staggered magnetization. So how does it change? And so this distribution changes from, well, actually, in this case, I guess it's not easy to see the difference between simply adding a few holes or just doing like full string theory. But if we go to like at 5%, we're still close enough to half filling, but at 20% filling, we see that the distribution of staggered magnetization also changes quite dramatically. Experimentally, and again, it's still consistent with this kind of string picture of spin and a hole and bound together. So I say that at this point, it's a fair statement that it's kind of this picture of, well, you can call it a hidden order. The idea is that if we could undo the motion of a hole, we would see that spins still have the same correlation as they used to have at half filling, but the holes are moving so fast, they scramble the spin. So if we just look at two-point correlations, correlations look completely different, right? Say next nearest neighbor changed from antiferromagnetic to ferromagnetic. But in reality, on this kind of original, in original space, before we include the motion of a hole, we still see the same spin texture. So I think it only is the beginning of, learning more about the system, because I would call it, fortunately, the temperature is still high enough that we can study sort of magnetic polarons in isolation. Interaction between them is not so important. As they lower the temperature, these polarons will have to self-organize. It's not yet clear whether they will self-organize in Cooper pairs to give us D-wave pairing, or they will self-organize into crystal to give us stripes. So we'll see exciting developments in this direction. And of course, you can also imagine all kinds of dynamical experiments, which in fact our colleagues are planning in the near future. So, okay, I think I'll just move on to my final remarks. So the focus of my talk was on dynamics. We really explored kind of, I would say, one corner, which is solid state systems and a little bit of cold atoms. But as you can imagine, it's a much more diverse field, like, like our dynamics of our universe, after all, is a non-equilibrium process, high energy physics. There is a lot of interesting questions in quantum optics when people are now beginning to prepare strongly interacting photons. Basically photons can become like hard coparticles, so they can make bound states just like matter. And we still have many challenges. I would say, from my perspective, the biggest challenge is that when we talk about dynamics of classical systems, we sort of have a certain idea of emergent paradigms. Like we know that there are some emergent structure like solitons, textures. When we talk about quantum problems in equilibrium, we also have ideas of paradigms like broken symmetry, Fermi liquid, maybe exotic topological states. But when we bring the two together, like if we take non-equilibrium dynamics and quantum many-body systems, it's still an open question. Is it really universal? We have some idea there are some emergent universal phenomena, such as many-body localization, topological states. We'll hear more about it in the school. But fundamentally, I think we still we study systems to a large extent on a case-by-case basis. But the question clearly on the back of our mind is, well, is there emergent universal behavior, just like in equilibrium, right? Or just like in classical systems? And I think that's exactly the reason why it's a good field for young people, so that there is a kind of a larger probability to make a strong impact. OK, thank you. But in reality, they're still there. They're just hidden by, by the holes reshuffling the spins.
Yeah, but I wanted to ask a bit different thing. If you look at the picture of those strings, Is it possible to observe some signatures of exactly a phase transition?
What do you mean? It's not really a phase transition.
It's a phase transition. At least at T0, there is an ordering at Hutton, and there is no ordering, log ratio ordering, I mean, at some small domain, I don't know.
Oh, okay, right. So in this case, right, well, still, as I said, this is a description which is valid at sufficiently high temperatures, right? And so it's a temperature where in 2D, right, so magnetic correlations still have finite range. It's not, so when...
If you go to zero.
But if I start going to zero temperature, my holes will have to self-organize. See, this whole description is built on the idea that we're at sufficiently high temperatures, where my antiferromagnetic state still has finite range correlations. And my polarons do not interact with each other. And that's how I can very easily connect. I can see that it looks like my magnetic configuration is basically the same as it was at half filling, except that it was reshuffled.
Now you need to introduce an interaction between polarons somehow.
So that would be the next step. Can we derive an effective interaction between polarons using the string picture?
We'll be very interested. It brings some analogies with quark motor.
Right, but obviously the question is, okay, even if I have attraction between two polarons, okay, will they attract the third polaron or not? Because if two attract, but the third one is not bound to them, then that's how we get pairing. But if they start attracting the third one, that's how you make stripes, or like even phase separation. So these are still questions which remain understood, but I think I sort of admit that maybe I don't believe we're smart enough to just write this solution. That's why I think it's, I prefer the route of being guided by experiments. We're trying to find the kind of the best simple model which can explain the data that we find from experiments.